All right. We did it. Show starts now. The rice maker is on, so dinner is in the works, and now it's time to do the show. So, hey everyone, welcome to the Monday live question show. This is, of course, the raw material from which we craft the weekly question show. And this is your chance to participate, to make this show what we all know that it can be. But, so go ahead, just post any questions that you have in the chat, and Nancy Graziano and the army of moderators will find those questions and feed them into the database so I can see the questions in a very concentrated manner, and then I can just hammer out answers to these questions as quickly as humanly possible. Now, there's going to be am I still asleep? Maybe. There's going to be, are you all just a dream? Is that what the possibility is? So just keep in mind that the people who I will be giving okay, so like I might not answer your question. First, we get a lot of questions. Typically 5 to 10 times as many questions as I'm able to actually answer. So I'll answer them as quickly as I can, but man has his limits. But we'll go through the main show and I'll finish the recording, but then stick around because we'll do overtime for as long as I have energy. Or I guess after the rice is done. Now, I will put my priority on the people who have never had a question answered before. So I can see how many times I've answered your questions in the show, and it's actually gone out in the final published show. And for people who've never had a question answered before, I will try to put emphasis on those questions. I may not know the answer. Like, I'm just a journalist, not a scientist. And so if the question is very esoteric or very like, what is your opinion of string theory? Like, I don't know. I'm just a journalist, man. And then if the question is like very complicated and requires research and requires me to look up some information, I may or may not answer the question. It depends on how exciting the question is. And so if the question's like really exciting and I feel like I can get the answer really quickly, then I will quickly do a little bit of digging so that I can give you a good answer. But if it's like, if you're asking me to calculate the habitable zones of 5 different types of interstellar objects, no. So that's the criteria. All right. Now I've got a bunch of prepared questions that were in the YouTube comments. So I'll get to those first, and that'll give you all time to ask your questions and get them into the chat. So, let's get started. Okay. All right, start my recording. Yes, I am recording. All right. All right. It's time for the question show. Your questions, my answers. Now, as always, wherever you are across my channel, start the whole thing again. It's time for the question show. Your questions, my answers. Now, wherever you are across my channel, if a question pops into your brain, just write it down. I will gather them up and I'll answer them here. And just another reminder, we record the show every Monday at 5 p.m. Pacific time live on YouTube. So if you want to be part of the live show, you're going to see somewhere around here the event for the upcoming show for next Monday. So make sure you subscribe to the channel, click the notification bell, and I promise YouTube will notify you when we go live and you'll be able to come and join. There's no way that you will get your notification an hour or day later from when the show actually went live. But if you are sort of nervous about it, remember Monday, 5 p.m. Pacific. All right, let's get into the questions. Andrew M. I love listening to this when I go to sleep, but I have a problem. Suppose the ISS adds a module that's a big room, a sphere for argument's sake, and you somehow found yourself in the very middle of the room with zero velocity in any direction. The walls are, say, 5 meters away from you in each direction, and in this scenario, could you swim through the air and actually escape, or would you be stuck in the middle since every action that you make has an opposite reaction? Would this be any different if you're floating outside in space? If you could not eject material, would you just be stuck forever in the same spot or orbit? All right. Wake up, Andrew. This is not sleeping time. This is learning time. All right. So you've got this scenario. You've got this astronaut. They are in the middle of some kind of sphere, in the space station. It is filled with air, but they have no easy way to get themselves to the wall of the station. And so the question you're asking is, would they be trapped in this sphere forever? And the answer is they could get to the edge. Now, you're exactly right that when you're in this zero gravity environment, then typically the way you would need to be able to get around is you would have to throw things off of throw your shoes, and you would get a kick in the opposite direction. But the key is that you're surrounded by air, and air is a fluid, like water is a fluid. And so you could theoretically swim through the air. I mean, birds do it, right? They flap their wings and they swim through the air. Now, of course, there's a lot more going on, but you could do it. Now, the density of air is about 1/781th. Is that right? Yeah, all right. The density of air is about I'm trying to think of a good way to describe this. All right. The density of air is about all right, one more time. The density of air is about 1/781th of water. In other words, water is 781 times more dense than air. And so you could theoretically, with hundreds of times longer, swim through the air across to the other side of the room. So it would be hilarious, right? You would be doing the breaststroke in the middle of the air. You would be trying the front crawl. Now, it wouldn't exactly, I think the breaststroke, think about the kinds of strokes you can use when you're swimming underwater, when you got water above you and below you, which is different to when you're doing the front crawl in water and your arms are sometimes in the water and then sometimes in the air and you're sort of pulling it. So yeah, you could breaststroke or underwater swim your way to one of the walls. It just might take you a couple of hours. I don't know exactly how long it would take, but it would take you much longer. But then the question you asked, a follow-on question to that is, let me do one other thing. Now, if you could do anything to increase the surface area of your hands, then you could speed up the process. So if you maybe took off your socks and put them over your hands, or if you built yourself some kind of makeshift flippers, then you could get to one of the walls a little more quickly. But it would be hilarious and it would take you a long time. But the other part of the question is, what happens if you were put outside the space station? Would you be able to swim around? And this is where we're getting a lot closer to the fact that you're going to need to kick off some kind of propellant. You're going to need to throw a shoe. You're going to need to spray from a fire extinguisher, something to be able to give you a kick in an opposite direction. But interstellar space is not empty. But interstellar space is not completely empty. There are millions of molecules in a cubic meter of space. And so the density of interstellar space is about 1/10 quadrillionth the density of water. But it's not zero. So, same thing, if you want to swim around in interstellar space, you just need to be willing to take 10 quadrillion times as much time to cross the same distances. So imagine you're going to try and swim across a swimming pool size of interstellar space. What might take you an hour would take you 10 quadrillion hours because of how low density space is. So effectively forever, but it's not zero. And so, yeah, you could theoretically propel yourself in space by swimming through the interstellar medium. Okay. Oh, 100 quadrillion. Well, depends on where the space is. Okay. At Kablamo 9999. I don't consider the Fermi paradox to be a paradox. We have barely looked for life or technosignatures. How can we possibly draw a conclusion already? Whenever people give me a quick answer to the Fermi paradox, all right, the Fermi paradox, of course, this idea that the universe is big and ancient and there are countless stars in the universe where life should have formed, and yet we don't see any evidence of that life at all. And whenever I pose the paradox to people, I get some range of this answer that we've barely looked. And you're absolutely right. We have barely looked, but that's not what the Fermi paradox is saying. And let me give you the analogy of being here on Earth, right? When you are sitting in your room and you have in your heart, you know that you are about 2 meters away from a spider at all times. You didn't go looking for that spider. You didn't search every nook and cranny of the entire planet Earth to find that spider. That spider found you. That spider knew that it needed to be about 2 meters away on average from you at all times. So life has a way of getting around. And the assumption of the Fermi paradox is not that there are all these planets out there and we're going to have to go and search and scan them and find them and search for any kind of other extraterrestrial civilization. The assumption is that any civilization that gets to a certain level of technology will spread out to fill every single possible part of the galaxy. And even moving at 1/10 the speed of light, it would take an advanced civilization about 10 million years to send self-replicating spacecraft to every single star system in the entire Milky Way. All 100 billion stars would have the remnants of this ancient civilization, and it would happen in 10 million years. 10 million years is just a wink of the eye when you think about how long the universe has been around. So that's the heart of the Fermi paradox. Not why can't we find them when we look and we listen and we try to send out signals and listen for signals. It's why isn't the solar system crawling with robotic, self-replicating robot probes that have been sent by hundreds of civilizations that are across the Milky Way, and they're all trying to explore the Milky Way. And if your answer is for some reason why civilizations wouldn't do that, that's fine. But that also means that we won't do that, right? That no civilization, including us, will ever leave their star. No civilization, including us, will ever be able to send any kind of self-replicating robots to probes to explore the rest of the Milky Way. And so if you can't think of a logical reason why we won't in the future want to explore the universe using self-replicating robot probes that multiply at an exponential rate, then that is the limitation that you also have to place on us. You place it on other civilizations, but you also place it on us. And that is the paradox. Not why don't we hear them when we listen for radio signals? It's why don't we see them everywhere all the time? Like that spider that's just a couple of meters away from you. I should do the, right. Apologies, Chad. Now, I'm sure you've noticed these planetary codes that have shown up above my shoulder, and this is your way to vote for the questions and the answers that you thought were the best. And last week we had a tie for 2 questions. One, Holly Buckley asked if I could dive into the habitability of lava tubes on Mars, and J.M. Mellinson asked if I would be willing to fast forward to the future. And they were a tie, but like the fast forwarding to the future, that was the last question of the question show. So you are paying attention and getting all the way to the end of the show before you make your vote, which I think is awesome. You're not just necessarily voting for the first one. So once again, if you see that planet up and you like that question, vote at the end of the show for the question that you thought was the best. We'll count up all the votes and we will celebrate the winners, or in this case, the tie winners. Okay. David's Dream Factory. Is there a habitable... David's Dream Factory. Is there a potential habitable zone around a black hole's accretion disk? We're going to have to use the term habitable zone quite liberally here, but in theory, there are a bunch of ways that you can live in a habitable zone around a supermassive black hole. But there are a lot of downsides. But some of the methods for keeping your planet warm, I think you're going to find really surprising. So let's just sort of think about the idea here, right? You've got this black hole, supermassive black hole. It's going to have millions, maybe billions of times the mass of the sun. And the black hole is going to be rotating, and it's going to have some amount of material that is falling into the black hole and getting accreted. And as this material falls into this accretion disk around the black hole, it compacts together and it heats up and it releases radiation. And that radiation is useful for a civilization that is relatively close. And the key is that you want the amount of material falling into the black hole to be a very constant amount. Like in the same way that we want the output from the sun to be a very constant amount, the same thing you want with the black hole. If the black hole is feeding on stars and then not feeding at all and then feeding on another star, then you get these spikes in radiation that will change the size of the habitable zone significantly to the point that you are doomed. So you want to keep it just like whatever you do, you need to control how much material is falling into the black hole. So that's kind of like the main way. And, you know, I can't give you any hard and fast numbers. I mean, every object, whether it's a neutron star, whether it's a black hole, whether it's a white dwarf, whether it's a dwarf star, whether it's a regular star, whether it's a brown dwarf, like anything that is giving off heat will have a habitable zone, a place where liquid water can remain liquid on the surface. But just the size of that is going to depend on the mass of the black hole. And, you know, from my understanding in the movie Interstellar, when Kip Thorne and others did the math for the black hole in that, they actually calculated this point where that planet would be in the habitable zone of this supermassive black hole. I think it was like 250 million times the mass of the sun. So, you know, it was a pretty big black hole. So that's the first way that you could So that's the first way that you could have a habitable zone. But it's not the only way. So the next way that you could have it is due to general relativity, So the next way is due to time dilation. This fact that as you get closer to the black hole, then time slows down for you compared to the rest of the universe. Of course, in Interstellar, they were on this planet for a day, and when they came out, it had been 30 years. That was something like a 60,000 times acceleration of time. And that acceleration of time that you experience also causes a and that acceleration of time also causes a blue shifting of all of the radiation sources that are around this black hole. And so if you're going to have some star that is very far away and is giving off faint radiation in the red end of the spectrum, as you're close to the black hole, that light is going to blue shift and going to get into the visible light. And so you could very much have sources of illumination falling on your planet from stars that actually aren't part of the system. And if you get close enough to the black hole, the cosmic microwave background radiation itself will move into the visible side of the spectrum to the point that you could have the surface temperature on your planet be habitable thanks to the cosmic microwave background, which is in all directions and nice and even, and it's great. But you know, you're going to get very close to the black hole for this to happen. And the downside is that you're going to experience an enormous amount of time dilation. And so you might experience 1 year and the rest of the universe experiences 10,000 years. So you have to be okay with not being able to interact with the rest of the universe at the same level of time. Another possibility is that you have neutrino flux that is coming out of the accretion disk around the black hole that's going to be impacting your planet and potentially heating up the mantle and raising the temperature on the planet. And then the other thing is that there could be gravitational waves that are coming off of the black hole as it's interacting with other objects, and they are going to be deforming the crust of your planet and keeping it warm as well. So there's some combination of the heat coming from the black hole, the time dilated radiation coming from the entire universe, the neutrino flux coming off the region around the black hole, and gravitational waves. You can have some combination that someone might consider to be habitable. But all of the reasonable kinds of radiation that are going to get shifted into higher levels, all of the already extreme kinds of energy like X-rays and gamma rays, those are going to be pushed even to higher and higher energies. And so you're going to have some way to protect yourself from all of the downsides of being close to a black hole. But theoretically, all black holes have a habitable zone or various types of habitable zones. Okay. Marco Cambry, what are the highest velocity stars that have been recorded traveling? In the last few years, astronomers have found a bunch of objects they classify as hypervelocity stars. And these are stars that are moving so fast in the Milky Way that they're on an escape trajectory. They are on their way out of the Milky Way. And typically, that escape velocity is a few hundred kilometers per second. Once you cross a few hundred kilometers, the star is able to escape the gravity of the Milky Way and it's going to head off into intergalactic space. And the fastest star that's ever been seen is called US 708. And it is a hypervelocity star that is moving at 1,200 kilometers per second. And I'm sure we're like, how much is that? That's about 0.04% of the speed of light. So 0.04. Yeah, all right. And that's like 0.04% the speed of light. So you're not moving light speed, but still 1,200 kilometers per second is very fast. When you think about how the Earth is going 30 kilometers per second around the sun, 1,200 kilometers per second is a lot faster. And how could a star be going this fast? And the original idea was that the star had some kind of close encounter with the supermassive black hole at the center of the Milky Way, had some kind of three-body interaction with another star, and then it was kicked out on this enormous trajectory. But now that astronomers have been able to observe the star for a little while, they find that as you trace back the trajectory of the star, it's not close to the supermassive black hole. So plan B is that this star was once in a very tight binary relationship with another star, some kind of supermassive star. And so the two stars were whipping around each other, and then one of the stars exploded as a supernova and disappeared completely. And it was like a sling that then hurled the star out of the Milky Way. This is the fastest that's ever been seen, but chances are, as we make more observations, as Gaia continues to deliver science results, we will see even more examples of hypervelocity stars. So it's pretty amazing the extreme events that the universe can get up to all on its own. Okay. BB Benui. Will galaxies eventually fall apart and get dispersed, or will their matter mostly stay intact as all the stars die? We're at an interesting point in the history of the universe right now. When you think about the Milky Way, right? We have this large spiral galaxy that is made up of the mergers of many other stars. But we've got this other galaxy, Andromeda, which is hurtling towards us. It's just a couple of million light years away from us. And there are other smaller dwarf galaxies that are in our region. The galaxy M33 and Triangulum is going to be probably merging. And eventually, the Milky Way and Andromeda and all of the other galaxies in the local group are going to merge together into one giant elliptical galaxy. And we see other examples like M87, the galaxy where that other picture of a supermassive black hole's event horizon was taken, that is an example of an elliptical galaxy. They are giant, they are ancient, and they are dying. All of the gas that comes in that's used for star formation, all the sources are used up. And so all of the stars start to turn redder and redder. And eventually, in the longest amounts of times, they will just wink out one by one until the star, over the longest scales of time, they'll just wink out one by one until the entire galaxy is dead. All you'll be left with is stellar remnants. You'll have black holes, you'll have neutron stars, you'll have white dwarfs. But this giant collection of objects will still be held in some kind of gravitational equilibrium. They'll still be bound together gravitationally. And because all of the other clusters of galaxies, all the other local groups, these collections of 10 to 20 galaxies, they're all being accelerated away from us thanks to dark energy. And so the amount of gravitational influence that can come to us over time will go down and down and down. But you will still have gravitational interactions between the individual objects in the galaxy. And so we talked about these idea of these hypervelocity stars. As they get too close to the supermassive black hole, they will get a kick. And so you'll have some percentage of objects will find their way down to the middle of the galaxy and they will go into the black hole. Or they will find their way down into the center of the Milky Way. They will encounter some kind of three-body interaction with another object and they will be kicked out of the galaxy, hypervelocity star, and they're going to be off, never to return. And so when you think about the farthest future of the universe, of the Milky Way, it will be black holes and then stuff that was kicked out that never got to be turned into a black hole and nothing else. I mean, there might still be some kind of debris, but if you wait over just incredible deep time, things will find their way into black holes. Black holes will find their way to each other. And eventually just the universe will be black holes and stuff that was kicked out on escape velocity trajectories. Night family, can you do a brief explanation of the Hubble tension and why it's a crisis? Now, we just did an episode of Astronomy Cast this week all about the Hubble tension and the crisis in cosmology. So that's the long version. That's the 25-minute version. So the short version, when you measure the expansion rate of the universe in our local area, when you measure it to nearby galaxies, you get one number. And when you measure the expansion of the universe in the cosmic microwave background radiation, you get a different number. And those numbers don't agree, and their error bars don't overlap. And so either we're measuring the distance to these objects wrong, which is highly unlikely, or there's some kind of new physics that the universe changed in the rate that it was accelerating its expansion. And the way I like to think about it is like, if we imagine the expansion of the universe before the discovery of dark energy, then you imagine you're driving in a car and you hit the accelerator and your car speeds up. That's inflation. And then you take your foot off the accelerator and your car just slowly coasts to a stop. And that is the future that astronomers used to think. And then when they did their observations and they found dark energy, what they found instead was you put your foot on the accelerator and then you take your foot off the accelerator, but you still leave it on just a little bit. And over time, you just keep speeding up faster and faster and faster forever. But maybe it's that you put your foot on the accelerator a little bit and then you take it off, then you put it on a bit more and you take it off. And there's something going on in that time between the beginning of the universe and the most recent time. And that is the tension between these two measurements of the expansion rate of the universe that don't agree and are both so accurate that there's no wiggle room to say, well, maybe we're both wrong enough that our answers overlap. That's gone. The error bars do no longer overlap. And that is the crisis. And crisis is a terrible name because it's like it's not the crisis in cosmology. It's the wonderful opportunity for new physics to be figured out in cosmology. And whenever you talk to astronomers about it, they're just so excited. They love that this field that felt so deadlocked for the longest time, there's now wiggle room here to try and figure out more physics for how the universe works. I still feel like that was too long. Tony Wells Fraser, what do you think about the inner core that has stopped spinning nonsense in the last week? So if you notice, we haven't reported that on Universe Today. Not like you check every story that we report, and I didn't mention it in Space Bites, and I probably won't. It feels fishy to me. Feels a little weird. It's one group of researchers. I haven't heard other people back up this observation. It doesn't feel really rock solid, pardon the pun. So I'm going to wait. In the immortal words of Paul Sutter, if it's interesting, it's probably wrong. And the idea that the inner core of the Earth changes direction every few decades is really exciting and really weird. And I'm going to need some more evidence before I stick my neck out and report this as news. So now you're seeing behind the scenes about how my brain works as a journalist. So I understand that I'm missing out on the opportunity of reporting the story while everybody else is doing it. It was on Boing Boing today, but that's just my choice as a journalist on which stories I want to cover. And that's kind of the, that's the decision criteria that I make. And when I see an interesting piece of news, I kind of go like, what, how do I know this is real? So that's my position on that. And hopefully, as you've been watching my content, you have that same instinct. You're like, even the way you ask your question, you're just like, is that nonsense or is that real? Shadow Mask. Fraser, I have a hard time imagining Starship as a human-rated launch vehicle because of its unusual design and hair-raising reentry profile. Do you have more optimism than I do? And if so, why? I don't really know the answer to this question. Like Starship, for sure, is unusual. It is a fully reusable two-stage rocket where the first stage, the booster, returns back to Earth, and the upper stage goes all the way up to space and can re-enter the Earth's atmosphere and return to a landing. And the way the rocket is developed, there is no escape point. So while with, say, the Space Launch System, there's like this little nose cone that sits at the very top of the rocket that if there's a problem, they can fire this and they can get away from the exploding rocket and carry everyone to safety. And that does not exist. So if the Starship is attached to the top of the booster and the booster starts to explode, there's no way to get away from Starship. But Starship can detach, fire its rockets, and get away from the booster. And I'm sure they're going to build that in. So it doesn't have an escape pod. It is the escape pod. But if there's a problem with Starship itself, well, then, that's a problem. The re-entry profile, I 100% agree with you. That would be super unsettling. Like when you watch Starship return to Earth and it's belly flopping down through the atmosphere, doing this, and then at the last minute it kicks down and lands. Like, can you imagine being on it when that happens? Like, imagine you want to just take a trip across planet Earth and you've decided to take the Starship option because you can get anywhere on Earth in an hour. And so you and grandma, right, are upside down and then hurtling around and the G's are extreme, but you got there. I'll take the slower flight, please. But we don't know what the safety and reliability is going to be in the long term. This is an unknown question right now. And it's only through watching these things fly many, many times will we have some kind of understanding of whether or not these things are safe. I mean, spaceflight is never safe. So it'll never be as safe as like an airplane. But when you look at the reliability of the Falcon 9, that's pretty good. But even if it turns out that they can just never make this thing as safe as they want, once you get into orbit, then your safety requirements change dramatically. And so maybe people will get on a Crew Dragon. You'll have 7 people on board the Crew Dragon. It will fly up to space, dock with the Starship. Everyone will get off the Crew Dragon and into Starship, and then fly around in space. So I think there's workarounds to go through that. So I don't really know. I mean, thousands of very skilled engineers at SpaceX are putting their reputations on the line that this is going to work. NASA has purchased a contract with SpaceX to land astronauts on the surface of the moon, although the moon is different from landing on Earth, but still, that's a part of the puzzle. So, there's enough people that are confident, who I trust, that this is going to work, that I'm not skeptical. I am optimistic, but I'm also open to us discovering that the whole idea is completely flawed. So I don't need to choose. I get to just wait and report on what happens. Andrew Lodmill, are you feeling positive about sufficient government space and science investments in the future? Will private companies invest more in the future? Obviously, we are seeing an increase in private investment into spaceflight. I mean, look at the fact that SpaceX has launched thousands of Starlinks, plans to launch tens of thousands more. That's just one network. You've got what Amazon is going to be doing with their Kuiper network. You've got the Russians are going to be building their own network. The Chinese are going to be building their own network. Like, within a few decades, there are going to be tens of thousands, if not hundreds of thousands of satellites in low Earth orbit. And I don't want to get into the ethical issues of hundreds of thousands of satellites in low Earth orbit. There's all kinds of risks there. But will private companies be willing to, if there's money to be made, they will be spending money. So I think we're going to see just a continued dramatic uptick in the amount of rocket flights that are going on. But you're talking about government space and science investments, and I think that's steady as she goes. I mean, we've seen NASA's budget remain largely unchanged for decades. It's around $20 billion a year. Sometimes it's a little bit more, sometimes it's a little bit less, but that's the number. And the thing that's new is you're seeing larger and larger investments from other countries. China has launched as many rockets a year as SpaceX does, and they've launched tons of they've launched a space station. They're going to be launching their own space telescope, and they're investing in developing into reusable rocketry. And of course, their long-term plan is to send humans to the moon and eventually Mars. But you've also got nascent government programs in a lot of other countries. The Koreans have launched their first rocket. Japan launches rockets. India does a great job of launching rockets. And then you've got places like Virgin Orbit operating out of the UK, although their first rocket didn't do so well. There's going to be a rocket launch pad here in Canada. And then you've got all of the various governments that don't necessarily have launch facility, but you've got things like various places across Europe are building hardware for satellites and crews to the various space stations. Obviously, Europe has their launch center down in South America. So, Europe has an increasing amount of investment into space exploration. You've got United Arab Emirates with their mission to Mars. So there's a ton of investment. Israel has some private companies. The Bereshit lander was built out of Israel. So I think what I find really exciting is that with the miniaturization of technology, with the lowering cost of access to space, you're seeing many countries around the world able to start developing their own space agency at whatever scale they want. Maybe they're not going to build the full stack from rocket to payload, but maybe they're just going to build payloads, or maybe they're going to provide rocket services. So yeah, I mean, I think it's just becoming more and more evident that access to space is important for any nation, and they need to invest in developing both the expertise as well as the technology to play a part in whatever future that holds. J.M. Milson, did you ever visit the observatory in Victoria, BC? Yeah, absolutely. The center of the universe. I think that's what they called it. The not the H. Millen. That's one in Vancouver. I forget the name of the observatory in Victoria, but yes, I've been to it. I think they shut it down. Michael Harmer, how do you observe dark matter? Well, obviously you can't observe dark matter because it's invisible. So you have to observe the gravitational effects of dark matter. You can't observe dark matter because it's invisible. So you have to observe the gravitational effect of dark matter. And there are many different ways that astronomers actually observe the existence of dark matter. Now, the first one is they infer its existence through the rotation curve of galaxies. So they look at a galaxy, they see how quickly the galaxy is rotating. They can measure that. They measure the redshift of the stars on one side of the galaxy, they measure the blue shift of the stars on the other side of the galaxy, and from that they can tell how quickly the galaxy is rotating. And when you punch in the number of stars in the galaxy against the rotation rate, the galaxy should be flying itself apart. And so since the galaxy is not flying apart, you can infer that there is this dark matter that's there. But the main way that they actually observe dark matter is through gravitational lensing. And what astronomers will do is they will map large chunks of the sky and they will look for how the light in that area is being warped. And what they can tell is that there are galaxy clusters and even just blobs of dark matter that are out there that are warping the light from more distant objects through its gravity, like a natural lens. And they can map that out with such efficiency at this point that they can see, like, here's the galaxy cluster and here's the larger weird irregular shape of the dark matter halo that the galaxy cluster is embedded within. Or here is a galaxy that has no dark matter or almost none. Or here's a galaxy that is almost entirely dark matter and has almost no stars in it. They can map this through the gravitational lensing by making these observations. So it's really quite amazing how well they can do these observations while they don't necessarily know what it is. And the thing that I love is that, because of the amount of gravity that dark matter is going to add to a galaxy cluster, right? It's like a factor of 10. So if you have the gravity of a galaxy cluster and then you add the dark matter, you get 10 times more. You get a really powerful natural lens that you can use to magnify objects that are more distant. And so we don't know what dark matter is, but we use it as a telescope because we know where it is, we know how much it is, and we know what effect it's having on the observations that astronomers make. So you can't observe it directly, you can just measure that it's there. And that's why it's so tricky to know what it is. That it could be a particle, it could be that we don't understand gravity at the longest distances, some combination in between of many different objects that are invisible. And it's made the search for dark matter really tricky. But it's out there, and eventually someone will figure it out. Sorry? Dr. Sloth, could dark matter be neutrinos? Maybe some, but the problem is that neutrinos move too quickly, and so they wouldn't clump up in the way that dark matter does. Whatever dark matter is, it has to be moving slowly, and neutrinos move almost the speed of light, so that wouldn't work. Weird. Okay. Am I missing questions? Okay. Don't understand your question, Tim 871965. 17 million years for the universe to be able to form ice, but over 300,000 years before the light is able to escape. So we had ice before light. No. The light could escape at 300,000 years after the Big Bang, and then the entire universe could have been ice up to 17 million years after the Big Bang. So that's light before ice. Bravo 01, could you make a phone call from low Earth orbit with a regular iPhone? No, but almost. Almost. Like theoretically, you could. Like there is a satellite by a company called Lynx where they were flying the satellite overhead. And so, it was a low Earth orbiting satellite. And as it was a CubeSat, so it wasn't very big. And as it was flying overhead, it was connecting to phones that were searching for Wi-Fi. And it was just making these connections and dropping them and making these connections and dropping them as it was flying overhead. So yeah, a spacecraft flying overhead can communicate. And I know like with the new iPhone, they've got the ability to make emergency calls and other stuff like that. So, so theoretically, could an astronaut make a call on their iPhone? I mean, they would need to have a special tower directed at them, and then they could. Jeff Wamble, can we ever know the origin of the solar system? That is, the supernova whose remnants we came from. Does our sun have any siblings? We assume that the sun formed in a stellar nebula like some of the other stellar nebulas that we see out there. Like when you look at the Orion Nebula and you see hundreds of stars forming together in this vast cocoons of gas and dust, that is what a very young star system would have looked like. And then you can see examples, say, of the Pleiades star cluster, where the stars have ignited, their light is blasted away most of the radiation in the area, and the stars are now just revealed. And that's like a few tens of millions of years down the road of this process. And so we assume that the solar system was part of one of these stellar nebulae and that we had siblings. And then over time, gravitational interactions between all the different stars added up, as well as the interactions with other stars that were coming close, and they plucked away the stars from our star cluster one by one and then started to spread them around the Milky Way. And it's tricky to find them, but astronomers do think they've found potential siblings for the sun. And so there's like two pieces that they're looking for. They're looking for the velocity, they're looking for the trajectory of a star that is similar enough to the sun that in theory they could have been overlapping in the past. And then the other thing they're looking for is the chemical signature of the star itself, because it would be assumption that the stars in our nebula were roughly made of the same kinds of ingredients. And so if you found a star that had very similar chemical fingerprint to the sun and it was in a very similar orbit to the sun, that those might have been part of the same solar nebula. And I know there was like one, in fact, I think I did a video about this here on the channel, that one of the sun's siblings has been found. And astronomers did that. They looked through the Gaia data for all of the stars that were in a similar trajectory of the sun. And they looked through this other database that holds all of the chemical fingerprint information and found stars that were very similar to the sun, looked for how they overlap, and they found one star that appears to have been formed in the solar nebula. But chances are there are dozens, if not hundreds, of other stars out there that formed with us. It just could take time. I mean, they could be on the other side of the Milky Way at this point to be able to find them. Now, we don't know exactly, it wasn't one supernova that formed. Like when the solar nebula started to collapse down, there would be these heavier stars that would have detonated as supernovae, one after the other. Multiple stars probably did this. And so each one would have embedded their material into the solar nebula and enriched the rest of the stars that were there. But we do know that a pair of neutron stars must have collided in our vicinity a few million years before the solar system formed, based on the amount of various heavier elements that we have here in the solar system. So it's going to be really tricky, maybe impossible, to try to roll back the series of events that happened early on in our solar nebula. But it's not impossible, based on the various kinds of heavier elements that we find here on Earth. If we find them on other places, maybe we see other stars, maybe you can start to build this database and go, well, first this star went supernova, and then that star went supernova and enriched it, and try to sort of tease out the chain of events that led to our solar system becoming the place that it is today. David King, how long till we have sports on another planet? Imagine football on Mars. Yeah, I mean, there's sports that we have here on Earth, and we can imagine versions of them on Earth. Football on Mars with one third gravity, where like it would be a very different game, because it would be trickier to run. If you tried to run or jump, you could jump 3 times the height, but it would be harder to run at a faster speed, because each step that you take, you'd be taking bigger leaps into the air. And so running would be very peculiar, but it would be relatively easy to jump over other people who are trying to stop you. But imagine other games, soccer, where you would be, I guess football, you're imagining, like, I got to break this up, right? We're talking about American football, we're talking about soccer, we're talking, anyway, every sport is going to be different. Hockey, that would be crazy. But I like the idea of sports that would be possible on other places that we can't have here. Like if you're on the moon, you're in 1/6 Earth gravity. In theory, you can slap on a pair of wings and you can fly around inside an atmospheric dome. And so you can imagine some sort of game where people are flying. You can imagine races where people are flying with their wings on their arms. So it's inevitable, right? That as soon as we have people living in space, in fact, I'm sure astronauts have already come up with a variety of games that they play on board the International Space Station. But then as over time, as we get more and more larger spaces for them to work in, we will see games. And eventually, those games will become professional, and we will have leagues that we will watch. I mean, I think the interesting thing is going to be when we have games in zero gravity. Like, think about, say, an Ender's Game. They had these games that they played with zero gravity, and they had to think in 3 dimensions and jump from place to place. That would be really cool, and I look forward to that. So, yeah, I mean, we need enough space to play the sport, and so that's going to be the limiting factor. It's going to be decades before we have large enough spaces that people can play sports inside. But once we do, it is inevitable that people are going to do this. Asmund, do you have a favorite quantum mechanics interpretation? I get this kind of question all the time. Like, just a journalist. I have no opinions about that kind of thing. Like, I can tell you what people think, but I can't. But I don't have an opinion because I don't know enough. Because I can give you opinions on how to run a space news website, how to be a journalist. that's where my ability to have opinions about that kind of stuff ends. And so I will always avoid that kind of stuff. Isaac Catone, is the Nancy Grace Roman telescope somehow linked to null? I don't understand the question. So can you give me more information on that? Scott Medchill. If Mars possibly had life a long time ago, does that mean that there might be oil under the Martian ground? That's an interesting question. Like, oil here on Earth comes from generations of plant life, mostly bacteria in the oceans, that fell down to the bottom of the oceans and then built up as sediments and then was subducted into the interior of the earth and crushed in the enormous heat and temperature and turned into oil. So, I mean, there are no plate tectonics on Mars, and I'm not sure there ever were. So can you have oil without plate tectonics? I don't really know. But if there was once life on Mars, then there would be layers of sediment at the bottoms of where those Martian lakes and oceans were, and you would find organic material down there. But I don't think it would be able to go through those other processes to turn into oil. And I think coal comes from trees, right? So you would need ancient forests, same deal, that they would have to grow and die and go into the earth and be crunched and smushed and compactified and then turned into coal. So I think you need those geological processes as part of the system as well. So like, we'll never explore Mars because there's no oil there. Kip Nielsen, does time dilation turn into a reversal of time as you pass the event horizon of a black hole? Not that I know of, but I mean, we of course don't really know what goes on. I mean, it gets you to infinity. Like, if you take the numbers and roll it in, then once you get into the event horizon of the black hole, and once you approach the singularity, you experience an infinite amount of time dilation, but you don't experience a negative amount of time dilation. You don't go into the past. You just go to infinity. All right, I'm going to wrap up the main show and then shift into overtime. So hang tough. Let me just finish up all of the admin stuff here, and then I'll stop the recording, and then we will continue on with the after show. So don't go anywhere. If you like my answers to your questions, as well as the other things we do at Universe Today, consider joining our Patreon club. This allows you to keep minimum ads for everybody. Like, as you can see, there are no ads in the middle of this video. As a patron, you also get an ad-free experience on universetoday.com for life, even if you unsubscribe. You get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Martin Per Morganson, David Walden, Steve Rafferty, Manfred Maniak, Dave Verbioff, Guillermo Furla, Dan Sutton, and Nick Knack. Join the club at patreon.com/universe today. All right, those are all the questions that we had today. Thank you, everyone who asked the questions in the YouTube comments, as well as everybody who showed up for the live show and asked your questions. Remember, we do this every Monday at 5 p.m. Pacific time, so definitely come and hang out. And don't forget to vote. Put in the planet for the question that you thought was the best. All right, we'll see you next week. Okay. If you want to stay on top of all the important space news, join my weekly email newsletter. I send it out every Friday to more than 60,000 people. I read every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Tim Whalen, Dave Verbeoff, Josh Schultz, and Andrew M. Gross, who support us at the Master of the Universe level. All your support means the universe to us. And now I've got to do my intro. Can astronauts swim in space? How is the Fermi paradox really a paradox? And how fast can stars travel? All this and more in this week's episode. All this and more in this week's question show. Almost said Space Bites. Okay. That's weird. One of the questions disappeared. Okay. All right. Kevin Sullivan, are there any good documentaries about the Fermi paradox scenarios as a list of the most likely reasons why the paradox exists? Recommendations. So there's a couple of recommendations there. Bob Hoppeldorf is saying the SFIA, so the Isaac Arthur series, is great. And then you've got Jean-Michel Gaudier's videos on the Fermi paradox. You've got some stuff from Cool Worlds that are great. So I would say those are three creators. I mean, I've done a video with Street Epistemology where I just defended the Fermi paradox for an hour and a half. And so if you want to sort of hear my most cohesive thinking on the matter, you probably want to search for that. If you do search for Fraser Cain, Street Epistemology, you'll get my defense. And the gist is that, the gist of Street Epistemology is to take a position that you believe and then explain the series of thought processes that go into why you believe what you believe. And so the thing that I defended is that we are alone in the universe, and then went through the process of the Fermi paradox. So I think that anyone who thinks they understand the Fermi paradox doesn't. Like, if the Fermi paradox doesn't freak you out, then you don't understand it, right? If you're like, come on, Fermi paradox, like, we've barely looked in the universe. Why would aliens want to communicate with us? All of your knee-jerk thoughts. I guarantee you haven't thought this through. Like, I know you think you've thought it through, but I guarantee that you haven't. And so I recommend that you seek people who have thought through these issues these flaws in the Fermi paradox that you have come to on your own, and you'll see that the whole situation is a lot more complicated than you believe. If I was to pick my favorite, I would say David Kipping at Cool Worlds has done some really interesting papers about the Fermi paradox that I find really compelling. So that's where I would go to. Yeah. Michael Harmer, could we ever use a nuclear space rocket from Earth? Yeah, absolutely. A Nerva rocket. We report on this week with a plan to launch a rocket in space, a nuclear thermal propulsion. But these work great on Earth too. You could launch a nuclear rocket from Earth, no problem. The problem is then you've got radioactive exhaust gases. You have to decide if you're willing to take those downsides. you go. Yeah. WFKU radio. Watch a couple of thousand hours of Isaac Arthur. He will explain the Fermi paradox. Yeah, that's the way you can go about it. Is you can just immerse yourself in the Fermi paradox from various creators, and I think you'll get to a point where you feel reasonably confident. And again, like the only outcome that I think you should have is that it freaks you out and you don't understand, right? It's like anyone who tells you that they understand quantum mechanics doesn't understand quantum mechanics. And I believe it's the same way with the Fermi paradox. Man, I've been doing a ton of interviews today and this week, so my voice is shredded. I've done 4 NIAC interviews so far. 2 of them are available already for for patrons. The one on building bricks on Mars and building a telescope that is thousands of kilometers across and floating in the L4 Lagrange point. I did another one on a new kind of fusion drive, and one today on a telescope that would find all of the Earth-sized worlds within 30 light years of us, just to directly image them all, a few dozen Earth-sized worlds. Let's see. So, John Suffel, how to go with the extension today? Were you able to use that okay? Kevin Sullivan, Isaac Arthur gets too much into the minutia for things to me to stay interested for so long. Well, some people want minutia, and so if you want minutia, Isaac Arthur's your guy. Kip Nielsen, do you picture a future where we send our consciousness to a drone on another planet in the same way that we log into a server on the internet? I do. Send out drone robots that can do stuff everywhere. Send our consciousness? Like when the singularity arrives and we upload our brains into the computers, then for sure we will be able to travel outward into the universe with our new robot bodies. And I've mentioned many times before that I'm just looking forward to my robot body. The issue is, would you be willing to upload your consciousness into your robot body if it was destructive, if it destroyed your brain? And that whatever wakes up in the robot body thinks it's you, but you don't get to continue your consciousness. So from your perspective, you die. And then somebody wakes up and they're like, I'm Fraser, and I'm going to go explore the universe with my robot body. No sale. I don't want that, right? I want to be the one. I want my consciousness to continue on. And so there needs to be some kind of non-destructive way, some kind of non-destructive transition where I slowly embed robotic neurons into my brain one by one and map my consciousness from the meat into the silicon. And then I shift over into my robot body. That's fine. I'm right now reading the 3rd book now of the Revelation Space. I could see this giant flaw with the whole book club plan, which is that someone suggests a book, but it's the first book in a series, so I have to read the whole series. And now the author is like my favorite author, and so now I have to read every book that they've ever written. So unfortunately, this is going to be my Alistair Reynolds year, and I wish I didn't have to do that, but I have to do that. So, because the Revelation Space is so good. We're up to 15 episodes of 3 Body on YouTube. Like, you can go watch the 3 Body Problem on YouTube if you want, with closed captions in English. So if you haven't already seen it, definitely check it out. Be wary when you watch it, because, it's a piece of Chinese propaganda, but it's cool. So just keep that in mind. Brother Sly, your consciousness as it is destroyed by chemical interactions. So the same? Well, maybe each Fraser that wakes up in the morning is a different Fraser, and the one who went to bed the night before has died. And like, if that's the case, then I have only existed since this morning, and I will die tonight when I go to sleep. But it doesn't feel like that's the case. It feels like my consciousness is continued. Diddly D, looking for that Lex Friedman podcast. Which episode? Is there a Lex Friedman on the Fermi paradox? I don't know if he's done it. It's kind of tricky. Like, I really like Lex Friedman, but I can't listen to his interviews about space. Like, I just can't do it because I just want to jump in there and ask questions, right? And he can't hear me as I ask him to ask these questions because the interview's in the past. And so it's too tough for me to listen to Lex Friedman podcast about space. I can listen to it about computers and lots of other topics. Leaf Binder, you can do a podcast with Lex? Sure, if he wants me. I'll be in the neighborhood in 2024, so maybe you'll have me on the podcast in 2024. He just did an episode with David Kipping, which is amazing. So, but I can't listen to I would love to listen to the one with David Kipping, but I know that I can't because I'll just jump in and I'll have questions for David. So, which I've already talked to David many times. So I've asked David my questions. Tom's Cubes and Games. If energy availability dictates the degree a civilization advances, will bet and zero by government take us back to the Dark Ages? What is bet and zero? I don't know what that means. So what is bet and zero? Like, increase in energy availability is kind of an inevitable, inexorable process that is moving forward. Oh, net zero. Okay, I see. Well, net zero. No, I mean, like what is... Okay, so here's the problem. When people use energy, like, say, burning fossil fuels, and they generate carbon dioxide, that is an externality. And when I take my garbage and I walk over to your yard and I dump my garbage on your yard, that is an externality. And when I pump the effluent from my pulp mill into the river, that is an externality. When I send a spacecraft into orbit that then shreds into little pieces and makes it more difficult and more expensive for other people to launch satellites, that is an externality. These are all tragedies of the commons. And the problem is that we don't account for the externalities when we consider what the cost is. What is the thing that is the most efficient for the free market? Like it would be cheaper for me to take my garbage and dump it on your lawn. That's cheap, right? I don't have to pay for garbage removal. Now, you might have to pay for garbage removal, but that's a you problem, not a me problem. And that is it in a nutshell. And so then if I say, well, if I'm going to throw my garbage on your lawn, but you're going to make sure that I pay to have that garbage cleaned up off your lawn and taken to the dump, well, now it's no longer the most efficient thing for me to do with my garbage. It's more efficient for me to get it to be removed in the first place when I consider the total cost and consider all the externalities. And so we just need to take that view. Like, are there hidden externalities in the way we run our lives that we are not taking account for, that we are taking for granted on what the planet delivers to us, right? The planet delivers us solar energy. The planet delivers us breathable air, clean water, plants that we can eat, animals that we can eat. Like, all these things are just like a natural process of the planet, and we extract from those things, and eventually various of those things will run out. There are no more passenger pigeons, right? We didn't consider the externalities of shooting all the passenger pigeons that we wanted to, or the dodos, eating dodos, right? You mean there aren't an infinite number of dodos? Or mammoths. And so I just think that's it. So like I don't know if net zero makes sense, But I think that properly measuring the externalities, properly accounting for the externalities of anything that we do will allow the free market to properly price in the various choices that we have, right? And so you don't get, I want to burn oil, and someone says, well, carbon emission's bad. Like, how bad? Well, okay, I want to burn oil, but I also have to extract the carbon back out of the atmosphere that I pump into the atmosphere. Now I know what it costs to burn oil. And then when I look at all the choices that I have for energy use, maybe burning oil is no longer the cheap one. Maybe solar energy, geothermal, hydroelectric, or maybe it is oil. Who knows, right? It might be that you can burn oil and extract the carbon dioxide again from the atmosphere, and it's the cheapest way to do it. So as long as you properly account for the externalities, but you can't just go la la la, I'm not listening, externalities aren't real. Like, they are, and they add up, just like me dumping my garbage on your lawn, right? At a certain point, you're going to go, hey, stop dumping your garbage on my lawn. This is my lawn, not your lawn. I need you to clean this up. So that's it. That's the that's my feeling on that. And so I think net zero is one way to approach it, but it's probably going to be more severe than that. We're probably going to need to do even more work to get the carbon out of the atmosphere to the point that we have a temperature regime that we find most efficient. And it's an economic thing, right? Like having to rebuild your beach because of rising sea levels, that costs you money. And so if you don't want to have to rebuild your beach, then you need less sea level rise. And the way you get less sea level rise is to have less melt in the poles. And the way you get less melt in the poles is to have the temperatures be lower. And the way you have the temperatures be lower is you stop putting so much carbon dioxide in the atmosphere. So that is my, and I think that every time we have these mismatches, it is because there are externalities that are not priced in. And once you price them in, you will have a much better understanding of what's realistic. Let's see. All right, we'll do like one more question. Evelina, my first time here. Question: if a civilization learns to make efficient fusion energy, doesn't that mean that a Dyson sphere becomes unnecessary? So you're thinking of having, like, extracting hydrogen directly from the sun and using it to make fusion energy, as opposed to surrounding the sun in solar panels. I don't know what the answer to that is. I mean, building up the infrastructure to be able to harvest hydrogen from the sun, like once you've used up all the hydrogen in Jupiter and Saturn, in Uranus and Neptune and all of the comets and stuff, then you're going to look at the sun and go, now how do I get the hydrogen out of that thing? So you're going to have to do that. So that's going to be some kind of machine that's going to be very complicated. But once you get that hydrogen out, then you're going to need to have fusion reactors that can fuse it. But the sun is pretty inefficient. Like, it is producing a lot of energy. That's just because it's got a lot of mass. Like a fusion reactor is vastly more efficient than the sun. And the other problem is the sun is only going to use a portion, like a third of the fuel in the sun will be part of the fusion process. And then the vast remainder will just be kicked out into the outer layers, will be just shed off into space. And then what will remain is the core of the sun. And so all of that hydrogen fuel is just going to be wasted. And so it would be much better. Like, the most efficient thing is if we figured out some way to extract hydrogen from the sun and make like 13 more stars, M dwarfs, around the sun. And then you would put them into some kind of structure that was gravitationally stable. And then you would just live for 10 trillion years around these tiny little M dwarfs. That's the most efficient thing to do with the sun. And so if you've got the technology and you may not even go that far. You might just like harvest light hydrogen from the sun and pile them up into Jupiter-sized planets that you orbit around the sun, or I guess orbit around other masses. And eventually you would, and then because then they're not fusing and they're not being used up, and then you can sip at that fuel as you need to. And so if we looked out into the universe and we looked for, well, like, why don't we see civilizations that have destroyed their suns and created little constellations of M dwarfs as opposed to suns? Like, this is the kind of thing that we would expect to see if there were other universe spanning civilizations, and we don't see any of that. The universe as it stands today, the Milky Way, the solar system, is not the ideal configuration for the maximum amount of energy use. It is barely the bare minimum to make life possible. But if we really cracked into it, we could do much better. We could improve the solar system dramatically if what we needed was more energy, right? At a terrible cost to the ecology of the solar system. All right. We saw the comet. So if you haven't already, I went and saw the comet yesterday and the day before, and it's mediocre, so not great. And then the moon is getting pretty bright, and it's sort of puffed out into this big blob in the sky. But if you've never seen a comet you have to see it in a pair of binoculars or a small telescope. But if you've never seen a comet before, now's your chance. All right, I'm going to wrap things up. So where do you look to see it? You look in Ursa Minor. So it's right beside the Little Dipper. So if you can find the Big Dipper, if you can find the Little Dipper, the comet is in there. It changes every day as it moves. So you find we have a story on Universe Today about the locations, but you can find lots of places where the position of the comet is related to all of those constellations in that area. But again, it's mediocre. Nowhere near as good as Comet Neowise a couple of years ago, and Comet Neowise was nowhere near as good as Hyakutake and Hale-Bopp. And I went on a rant earlier today about this. This comet, like, the universe has been failing us when it comes to bright comets. It can do better, and it knows it. So get with the program, universe. Show us those bright comets. You think making 13 more stars from wasted hydrogen? Okay, I think I'm out. What? You're out just because I went through the mental thought process of breaking the sun up into 13 separate stars? That's a bridge too far for you? All right. All right. Well, thanks, everyone. I'm going to wrap up. Thanks to all the moderators. Thanks to Nancy and the rest of the team that were helping gather those questions for me. That was awesome. And thanks in advance to Chad and Anton, who have to edit this nightmare. And we will see all of you next week. Thanks, everyone. Where is the button?